Hello guys, welcome to PLC Goods video tutorial. In this video we are going to learn input-output instructions, which are an important group of RSLogix 5000 instructions. First, we will see how a message instruction can be used to connect two controllers together. After that, I will explain the get, set, system value instructions. Then we will see what the immediate output instruction is. Then we will define and do a practical project to learn application of these instructions. Let's start with the message instruction. Remember, we wrote a program to turn on 8 cabinet fans. We use this input-output module to get signals from the door limit switches, temperature sensors, and start push buttons. Also, a module is used to turn on 8 fans. We use this virtual PLC station, but in real conditions, we will need to connect 32 devices to input terminals of a PLC by wiring. Now suppose there is another controller that must be connected to temperature sensors, limit switches, or push buttons. How can we do that? An unsuitable solution is using another digital input module and doing the wiring process again. The better way is to connect the second controller to the first controller to request its digital input status. In this way, we won't need to rewire equipment again. We need to connect two controllers together. Industrial processes usually use an Ethernet network, but if you don't have any real processors, don't worry. In this video, we are going to connect two virtual controllers which can be created by RSLogix Emulate 5000. I will insert another controller into a virtual chassis to show you how these two controllers can exchange data between themselves. Here you can see RS links that can connect my computer to this virtual PLC station. The virtual chassis has a virtual controller and input-output module. I configured this hardware in RSLogix 5000. Also, this is the program that can turn on/off the 8 fans. Now let me insert another controller into a virtual chassis. The second controller can connect to the first one via the virtual chassis. Now I right-click on the RSLogix 5000 icon in my taskbar menu and click here to write a new program for the second controller. First, I select my controller type, RSLogix Emulate 5000 controller. Then I select the revision number, which has been selected for the second controller. Here I write second controller as the name of the new controller. Finally, I should determine the slot number of the new controller. Here you can see the second controller which I installed into slot number 8. Note that I also need to determine the first controller type and its slot number. Okay, I configured the first controller for the second one. Similarly, I can configure the input-output module, but I don't need it because the second controller can use its data via the first controller. At the beginning of this video, I showed you the first controller program which was tested in the previous video. Now let's write a program for the second controller. First, let's select the input-output group of instructions and insert a message instruction. This instruction reads or writes data asynchronously to another module like a CPU module on a network. First, I should create a tag for that. Its data type should be message. This is a type of data that includes a lot of parameters like counter or timer data types. Note that this tag cannot be created under the main program folder. It can be created only in the controller tags table. I created the new tag in the controller tags table and I can see its parameters. Now let's learn how to use the message instruction. Click here to open the message configuration window. There are several items under the message type menu to make a connection between a RSLogix 5000 controller and another controller type. In this project, we use two virtual controllers created by RSLogix Emulate 5000. So I need to work with these two items, CIP data table read and CIP data table write. Let's select the CIP data table read item to get data from the first controller. Another type can be used to send data to the first controller. Here I can select the tag from the first controller which I need in the second controller program. Let's see the first controller program. Here I can select any tag or address which is defined in the controller tags table. The first controller is connected to an input-output module. Let's copy its digital input address. Note that it is defined in the controller tags table, so I can use it in the next controller's program. Now let's pass the selected address here. Then I should determine where this data should be saved in the second controller. Here I can select a suitable tag in the second controller or click here to create a new tag to save the received data from the first controller. Let me write a description for the new tag. Until now, I selected the source tag in the first controller and defined my destination tag in the second controller. Now, in the communication tab, I need to find and select the first controller. Now, if I activate the message instruction, it will read the selected address of the first controller and save it on a tag inside the second controller. Here, let me use the enable bit of the message instruction for the normally closed contact. It makes to enable the message instruction automatically. Now let me use a compare instruction in the second run. I want to compare the saved parameter in the second controller with 0. If I activate a digital input address of the first controller, then the received value from the first controller won't be 0, and the alarm tag in the second controller will change to 1. Let's download this program to the second controller. the message instruction is activating automatically in the first run of the program, and when I activate any digital input of the first controller, the second controller enables its alarm tag. Let me open the second controller tags table. Obviously, I can use any digital input of the first controller inside the second controller. Note that the second controller is not connected directly to any input-output module. It uses the input-output module data via the first controller. Let's select the input-output group of instructions. After the message instruction, there are GSV and SSV instructions: get system value and set system value. These instructions get and set the controller system data. We can use the SSV instruction to change the data in the attribute name field with the data specified by the source parameter. The GSV instruction works inversely. We can send system data to another address or tag. For instance, let's use the GSV instruction to see the scan cycle time of a processor. The scan cycle is the cycle in which a PLC gathers the inputs, runs the PLC program, then it updates the outputs. This takes some amount of time, often measured in milliseconds or microseconds. First, I must select the class name of the scan cycle data. This data belongs to the task class. Obviously, all program folders are placed under the task folder. Then I select the main task, which includes my program. Then I can select some data about my main task. For instance, last scan time or max scan time. Let's select the last scan item. This parameter is a number in microseconds that shows the last scan time of my controller. Then let's define a new tag to store this data. Alright, here is an error in run number 2 because I am in online mode. Let me exit from that and define the new tag again. Now let's download this program to the second virtual controller. Now we can see the last scan time of the second controller program in microseconds. Similarly, we can use GSV instruction to view and use other system data, or use the SSV instruction to change some parameters of the controller's system data. The next instruction is IOT, or immediate output. This instruction can immediately update a selected digital or an analog output module. The second controller doesn't have any output module, So let's test an IoT instruction using the first controller. After each scan cycle, PLCs update all outputs automatically. But if the scan cycle time is long, this instruction can be used to update all outputs of a selected module immediately. I recommend writing a suitable program to have a short scan cycle time instead of using the IoT instruction. This instruction is usually used for special and important outputs which must be updated as soon as possible. Naturally, I don't need to use this instruction because my programs are short. For instance, the scan time of my second controller program was about 150 microseconds. This time is less than 1 millisecond. We learned the input-output group of instructions. Now we are going to use them to improve the traffic light project. I used RSLinks to connect my computer to this virtual PLC station, which includes a virtual controller and an input-output module. Also, I configured the virtual hardware inside RSLogix 5000, and this is my traffic light program. Then I added another routine to create and use some tags which I used on this HMI screen. I designed this screen with FactoryTalk Studio software to display the state of the traffic lights in my program. Cars can move from west or south to east or north, and each traffic light has 4 states which are repeated every 40 seconds. In this video, we are going to use input-output instructions to improve the project. The second intersection should be controlled the same as the first one. Usually there is a delay when cars reach the second intersection from the first one. It depends on the speed limit. For instance, it can be equal to 5 minutes. So if we consider this delay in our program, and if a car is moving at the speed limit, it won't be stopped behind the red light of the second intersection. Let's assume the delay between the two intersections is 10 seconds to see the performance of the project faster. The second controller should be synchronized with the first controller. So let's open the first controller program to prepare data which must be sent to the second controller. First, I create a new program folder which will be executed after the main program one. By default, a program tags table is created for each program folder. Now I need a new routine. I want to send some data to the second controller. So I create a tag inside the controller tags table. I want to send 3 integer numbers. So let's create an array that can store 5 parameters. 2 parameters will be reserved for the future. I will use the first one to store my controller state. The second one to store the delay time. As I mentioned before, it will be 10 seconds, and the third one will be used to send the current time of the first controller to the second controller. First, let's see how a PLC program can detect its controller state automatically. Let's select the input-output group of instructions and insert a GSV instruction. Now let me use the help window. A GSV instruction can access these objects. For instance, I used the task object in the previous video. Inside this object, I can use the last scan time data. It gives me time in microseconds. In this video, I want to select the controller device object. This object identifies the physical hardware of a controller. Here, this parameter status is an integer number that represents the controller's mode using a special code. So let's store this code on the data tag which I want to send to the second controller. In the second run, I am going to use a move instruction to save 10 seconds on the data tag. The time is a number in milliseconds, and we know 10,000 milliseconds is equal to 10 seconds. Now I want to move the current time of the first intersection to the defined tag as the third number, which should be transferred to the second controller. Note that from the current program folder, I don't have access to the timer tag, which was defined and used inside the main program folder. So let me use a move instruction at the last run of the main program to move the timer's time to the third element of data tag. Until now, I stored 3 numbers on the data tag inside the first controller tags table. I want to use that in the second controller's program. Now let's download the current program to the first controller. I right-click on RSLogix 5000 icon on my Windows taskbar and click here to write the second controller's program. Let me create a new project in RSLogix 5000 because I need another virtual controller for the second intersection. Note that I want to use 2 controllers inside a virtual chassis. These controllers can exchange data using their common chassis. Naturally, for a real project, we need 2 chassis with 2 controllers for the 2 intersections which can exchange data using a suitable industrial network. Now I am configuring my virtual hardware in RSLogix 5000. After the hardware configuration of the second controller, let's write its program. First, let's insert a message instruction. I want to read data from the first controller, so I select CIP data table read. The data tag in the first controller includes three numbers which the second controller needs them. These three numbers represent the controller's state, the desired delay, and the current time of the first controller's timer. The data tag is an array with 5 elements. Now let me select the data tag and select its first element. After that, here I select number 4. So the second controller will have the first 4 elements of the data tag. Now let me define a similar tag inside the second controller to store data received from the first controller. Here I need to select the first controller. In the second controller, I want to divide its program into two parts. So I create two new subroutines. The first one with the name normal conditions will be executed when two controllers are connected together without any problem. The second subroutine with the name of fault conditions will be executed when the first controller is not in run mode. In this state, the second controller should turn on off its traffic lights independently. Let's open the help window again and look at the status parameter. Obviously, bits number 13 and 12 of the status parameters represents the state of the controller when the controller is in run, program, or remote modes. So the normal condition subroutine should be executed when these two bits, number 13 and 12, are 0 and 1 respectively. We have the status parameter of the first controller in the data tag. So in the second run of the main routine, let's use bits number 12 and 13 of the status parameters to jump the program execution to the normal conditions subroutine when the first controller is in run mode. Similarly, in the third run, let's direct the execution of the second controller to the fault subroutine when the first controller is not in run mode. The next step is writing a suitable program inside each subroutine. Let me just show you my final program for each subroutine. This is my program for the normal conditions subroutine. First, I used some math and compare instructions to produce the second controller's time using the receive time and a delay value from the first controller. Then I used some limit instructions to turn on the traffic lights at the second intersection like the program for the first intersection. Also, this is my program inside the fault conditions subroutine. In the first run, I used a clear instruction to turn off all traffic lights at the second intersection. Then I used an on-delay timer to have two flasher lights. Actually, I tested this program and I found two problems. First, the message instruction should be activated in each scan cycle to receive data from the first controller. So let's use its enable bit for this purpose. Then I should use bit numbers 14 and 13 instead of bit numbers 13 and 12 of the status parameters. Now let's download the program to the second virtual controller. These warnings are related to the digital outputs, which are used twice in my program. Let me continue. Now both of the controllers are programmed. Note that I need a little modification on the designed HMI screen to test and see its result. Traffic lights of the first intersection are connected to the first controller. Similarly, I need to create a new connection to connect the lights of the second intersection to the second controller. Pay attention, here I cannot see my second controller, so let's find and add it manually. I need to select the controller type and its revision. Here I should write the name of my second controller and to select the slot number of the CPU module. Now I need to connect each traffic light of the second intersection to its tag inside the second controller's program. Inside the second controller program, the red light is connected to bit number 2 of the output address. Similarly, I can connect the other traffic lights of the second intersection to a suitable tag in the second controller's program. Also, let me insert a numeric display to show the current time of the first controller. Here, let's select the accumulated word of the timer in the first controller. The time is in milliseconds, so I need to divide it by 1000. Let's test the project. The traffic lights of the first intersection are connected to this input-output module, and these lights are connected to this module. Let's change both controllers' modes to run. Note that when I click on the Start button, the first and second traffic lights start running. The second controller was started too, but it is not synchronized with the first one. There is a delay of 10 seconds between the two traffic lights. For instance, at this time, 20 seconds, the first controller changed this green light of street A to yellow. We will see this changing in the second intersection when the time is 30 seconds. Now let's change the first controller's mode to program mode. Obviously, the second traffic lights don't work based on the first traffic lights. The yellow and the red lights are flashing in the second intersection. I hope you have learned the application of input-output instructions. Now we are going to learn the alarm group of instructions which are categorized into digital and analog alarms. Also, we will learn what an alias tag is during a project for controlling a water tank system. This is my hardware and I configured it in RSLogix 5000. Here is the alarm group of instructions. The digital alarm instruction works based on the state of a digital address, but an analog alarm instruction works based on analog values. These two instructions work similarly, so I will explain only an analog alarm instruction. First, let me design a simple plant inside Factory.io to explain and use an analog alarm instruction. Let's insert a water tank from the right list and select analog mode for that. This tank has two filling and discharging valves and a level meter. Now let's design a simple control box. I insert two potentiometers to control the two valves and a digital display to show a water level. By default, the two potentiometers send a real number between 0 and 10 as a virtual voltage to the PLC. Now let's modify their names. I will use the first potentiometer to control the filling valve. The water level can be a number between 0 and 300 centimeters. So I need to select integer mode for the digital display. Similarly, let's change the second potentiometer's name. I will use that to open or close the discharging valve. Note that I want to control the devices with my controller, so I use the no failure mode for them. The two valves of the tank can be controlled by a voltage between 0 and 10 volts. Also, the level meter sends a voltage between 0 and 10 to the controller when the water level is changing between 0 and 300 centimeters. Now let's connect the tank and other equipment to the controller. In the configuration window, I don't need to change the controller's IP address or the slot number. In the I/O points section, I can define suitable tags. My equipment can connect to these tags, which will be used in the PLC program. I prefer to use the default tags, but I need to modify the count column. I don't need any digital inputs or outputs, but there are two potentiometers and a level meter which work with real numbers, so I need three analog inputs. Also, I need two analog outputs because of the two valves and one integer output for the digital display. The next step is to define these tags in RSLogix 5000 and use them to write the program. I configured the hardware here. Now let's define the tags which were selected in Factory.io in the controller tags table. Here you can see the real input-output addresses. Now let's define these tags. I will use them to connect the equipment in Factory.io to the program. Now let's write the program. Each potentiometer sends a voltage between 0 and 10 to the PLC. Also, each valve can be controlled by a voltage between 0 and 10. So I can use a simple move instruction to get voltage from each potentiometer and send it to the related valve. Now I want to remind you another way of using tags or addresses. Here the simple way is to use this tag, which I will connect it to the first potentiometer. It contains a number based on the potentiometer's voltage. But this tag is a little hard to understand the PLC program's logic. So let me define a new tag, pot filling. Now let's select an alias type instead of a base type. An alias tag refers to a base tag or another alias tag. Let's select the FIO real input 0 tag for the new tag whose type is alias. Now the move instruction goes to pot filling tag, which is recognized as an alias type. It refers to FIO real input 0 tag whose type is base. So the move instruction copies its contents to a destination address. Naturally, the pot filling tag is more meaningful than the FIO real input 0 tag. In consequence, it can help us to understand the program's logic. Similarly, let's use another tag whose type is alias, which refers to the filling valve. The move instruction uses the first potentiometer's voltage to control the filling valve. Similarly, let me use another move instruction for the second potentiometer to control the discharge valve. The level meter sends a voltage between 0 and 10 volts to my PLC. So I need to multiply it by 30 and send the result to a digital display. Now let me insert an analog alarm instruction. It has many parameters. First, I need to define a new tag for an analog alarm instruction. Note that the data type of the new tag should be alarm analog. Now I can determine an analog address or a tag as an alarm input. Its value will be compared with the alarm limits for detection. Let's select this tag FIOint output 0, which represents the water level, or select this tag digital display, which refers to the FIOint output 0 tag. The next parameter is program acknowledge all, which we can use to acknowledge all alarm conditions of an alarm instruction. Let's use the first real digital input for that. I can use the two next parameters, program disable and program enable, to disable or enable an alarm instruction. Similarly, let's use two real digital inputs for them. Now I need to enter the high and low limits directly or open the alarm properties windows to determine the limits. Let's determine these limits based on the water level. These limits can be a number between 0 and 300 centimeters. Naturally, the entered values should satisfy these inequalities. For instance, if a water level exceeds this level, its related bit inside the alarm tag will be changed to 1. Note that you can enable or disable each limit or change its severity. Severity does not affect the processing of alarms by the controller, but it can be used for sorting and filtering alarms. It can be a number between 1 and 1000. Its default value is 500. Inside the minimum duration field, I can enter the length of a time that an alarm condition should be detected before reporting an alarm condition. After that, a deadband can be entered to apply to selected levels. For instance, based on these values, if the water level exceeds 250, the alarm instruction activates a bit of a PLC memory, and if the level is reduced to 245, the instruction will clear that bit. Here we can check this box to require an acknowledgement for all alarm conditions. Also, we can define a class for our alarms. For instance, let's write tank as the class of the current alarm conditions. Sometimes the rate of changing is important. On the right side, we can determine the rate of changing in two directions, positive and negative. Inside the Message tab, we can write a text for each alarm condition and define a tag and use its value inside the text. Inside the next tabs, we can see general information like all alarm times, parameters, and properties of the selected tag for an analog alarm instruction. Note that an analog alarm instruction has many parameters. You can search for them on the help window and read their description. We can determine 6 alarm conditions with an analog alarm instruction. The instruction uses these 6 outputs to illustrate the state of an alarm conditions. For instance, it activates the first output when the water level is higher than 290 centimeters. Now let me use these bits of an alarm tag to turn on 4 real digital outputs. Let's verify and download the program to my controller. In this program, I use 3 digital inputs and 4 digital outputs of my real hardware. Now let me connect the equipment inside Factory.io to my controller. Factory.io is connected to my controller successfully, and it detected all defined tags in the PLC program. Let's test the project. First, let's open the feeding valve. I need to change my controller mode to run mode. Obviously, when the tank is empty, these two signal lamps are on because of two alarms of the four defined alarm conditions. Now the water level is 20 centimeters. The water level is low, but it's not under 10 centimeters, so only one alarm is activated. Let's check this condition in the PLC program. Obviously, only one alarm is activated. Now let's open the alarm properties window. Inside the status tab, we can see which alarms are activated and the time that the program detected them. Until now, my program detected only two alarms and one of them disappeared by increasing the water level. Now let's open the filling valve again. As the water level rises, another alarm is disabled. Right now, there isn't any activated alarm, but I can use the alarm properties window to see which alarms were happened already. These two alarms happened before. I can click on the acknowledge button to confirm that I know when the alarms were happened. Now let's raise the water level to 250 and 290 centimeters. It is expected the two other alarms related to high water levels will turn on the second and first digital outputs respectively. The two alarms related to the two high water levels are activated. Now the tank is full. Let's close the filling valve and open the discharge valve. Obviously, as the water level drops, one alarm goes off automatically. You can view and reset these numbers, which display how many alarm conditions were detected. I used the first digital input for the second parameter of the alarm instruction, so I can confirm all alarm messages using the first digital input. I hope you have learned how does an analog alarm instruction work. Thanks so much for watching this video. See you in the next one.